Important part of 3061 lib is odometry. That is knowing where the robot is on the field. That is done based on the various sensors related to the drivetrain subsystem in terms of the swerve modules and their positions, um, and then also the gyro as well that's used with the drivetrain, and then also the vision system and all the cameras and vision post estimates provided. 3061 lib has created a collection of related classes trying to achieve several goals at the same time. So the goals we're trying to achieve at the same time is we want to take full advantage of cross-the-road electronics, um, high frequency 250 hertz pose like odometry updates that's done within their code. And yet we also want to be able to completely replay um, based on our Advantage Kit log exactly everything that went on with our robot. And so that has added some complexity because it's tricky to reconcile both of those goals. We have decided to take a slightly different approach than that taken by the Advantage Kit across the road electronics templates. And we'll see more of that when we go into the drivetrain subsystem. However, for now, that's not too relevant, but I'll explain where those connections come up. So the robot odometry class here is an abstract class, and we'll look at the subclasses in a moment. And we created this class to to make a clear division of responsibility and not couple the drivetrain and vision subsystems together. So odometry related responsibilities belong to the robot odometry class. Both the vision and the drivetrain have references to this class. And then this class is responsible for providing estimated poses to all the code that needs it. We actually have two different pose estimators when we're dealing with our swerve drivetrain. There's the pose estimator contained within this class, technically it's subclass, and another pose estimator, which is the one maintained by Cross the Road Electronics. We call that our custom pose estimator, and we'll look more at that in a moment. The custom pose estimator is updated by Cross Electronics in their own thread below our hardware abstraction layer, so it does not participate. So that code doesn't actively run when we're doing a replay. We just read in those values as if we would from a hardware device. All of everything in this code, however, does live above the Advantage Kit hardware abstraction layer, and therefore supports tuning, debugging, and all those things that we highly value. All right, so this is a singleton class, and it has a reference to a custom pose estimator, which is optional. You don't have to have one, but we have one with our swerve drivetrain when we use cross-road electronics. We don't have one with our differential drivetrain, like with the XRP or anything. We have a couple tuning things here, include vision pose estimates and include vision pose estimates in custom estimator. You can turn these on or off. Certainly during competitions, they should be on, and for most of the season, they should be on. However, when we're tuning vision, figuring out things like latencies and stuff, we don't want the vision pose estimates fed into this pose estimator. Because it makes it hard to tune. And so we'll disable that so that we can look strictly at the pose estimator taking data from the swerve drivetrain and not having the vision pose estimates affected at all. So that's why these are set as constants. Here's our method to get the reference to the, oh no, I'm sorry, got ahead of myself here. This is the get estimated pose method. This returns the current pose of the robot. This is abstract because it needs to be implemented differently for both the swerve and the differential cases. We have an accessor method here to get the custom pose estimator. I'm sorry, to get the custom estimated pose from the custom pose estimator. And it will return a default pose if we don't have a custom pose estimator. We're able to reset the custom pose to the specified pose. This is important, for example, at the start of auto, perhaps. Um, and so we have a method for that. And then we have a method here that adds a vision pose estimate to this pose estimator. And so this code is actually the same regardless of whether it's swerve or a differential drivetrain. And so it's here in the abstract class. So the add vision measurement class, this is the same class you would see in the, for example, like swerve pose estimator class. We just have a couple extra things that we do here. For example, we allow the vision subsystem to provide an additional latency adjustment, which we will affect in terms of the timestamp reported from like photon vision, for example, and we'll log that adjusted timestamp. If we are including vision pose estimate, we call add vision measurement. This will be implemented by the subclasses. If there's a custom estimator and we're including vision pose estimates in that custom estimator, we'll also call the add vision measurement on that custom estimator as well. The custom estimator, which we'll look at in a moment, it assumes a different time base than what is used throughout the rest of the WPI lib ecosystem in terms of like pose estimators. And so we need to convert from the FPGA time base, which is what we use everywhere else in this code, to the current time base. And so there's a method here that we use to do that. That's a common sort like mistake, and then all of a sudden like nothing's working right with vision. So it's all got to make sure our time bases are consistent and as expected. If tuning mode is true, we do some additional logging. This is really helpful to tune your vision latency. And so what we do here is we use the sample at method to retrieve the pose estimate at a specific time. And then assuming we get one, we find the difference between where the robot thought it was at that time um, and where the vision pose estimate thought the robot was. And we log that difference and we log that past pose. So we can look at the difference and graph it. And we can visually look at the past pose and see where it is. Because the reason why this is important is when we get a vision pose estimate, by the time it is processed, by the time it makes to this code, it has occurred in the past. And so that's fine because the pose estimator classes we use are able to handle like adding in a pose estimate from some time in the past and refiguring out where we are in the current moment. But we want to be able to tune that and tune that latency from our vision system and be able to see if that is correct. And so, in an ideal situation, when we look at this, when we're tuning that vision latency, we would actually see the past pose from the pose estimator lined up exactly where the vision pose estimate is. And so usually when we're doing this type of thing to tune vision latency, this would be an example of when we would not be including the vision pose estimates because we don't want to quote unquote pollute this pose estimator. We want it to be based just on the what we get from the swerve drivetrain. And then we can compare where the vision says we are to where the robot thought it was and make sure those line up right on top of each other. Some other methods we have here, we can set the custom pose estimator. We do that inside of the drivetrain subsystem. And then here's the abstract methods that need to be implemented, as well as our get and set instance methods. The set instant is a little bit different than your normal singleton pattern. We just need to construct the subclasses in a more deliberate way based on which type of drivetrain subsystem we have that is the swerve or differential drivetrains. So that's why it's kind of odd that we have a set instance method here. We'll jump to that. So you can see here inside of, we'll get to this class later, but inside of the constructor for the swerve drivetrain subsystem, we pass in the swerve specific, the swerve robot odometry subclass and call set instance, whereas in the differential drivetrain, we do the same thing, but it's the differential robot odometry. So that's a little bit different between the two. But we don't want to get too far in the weeds there. So let's look at what these, let's look at the custom pose estimator interface first. So we created this interface, but right now we only use it with the cross the road electronics, their pose estimator. But here's a generic interface we could have, and it has all the standard methods that you might think, like being able to get the custom estimated pose, sample pose at, so at a given timestamp, what's the pose estimate for that point in time, resetting the custom pose to a specified pose, adding a vision measurement. And here's some documentation that goes in more that talks about the timestamp seconds here, is a timestamp with an epoch since system startup. Okay, so that's the current time. So you have to use that get current time seconds or do the FPGA to current time as we saw to convert it to the appropriate time base. So that's our custom pose estimator interface. In terms of the subclasses, we have our Swerve Robot Odometry right here. So the Swerve Robot Odometry class extends robot odometry and implements all of those abstract methods. It has internally an instance variable, which is a swerve drive pose estimator object. So all of this 3061 lib stuff, eventually uses the same WPI lib objects that are used elsewhere for pose estimators. There's just this additional logic on top of it. So we build the estimator just like one normally would. We rely upon robot config to get the kinematics, initialize everything to its default positions. We rely upon the estimator to get the estimated pose. So that's just a simple wrapper like facade type thing. Resetting the pose, very similar. We do go call back into the superclass to reset the custom pose, and the superclass that we were looking at before will handle that if there is a custom pose estimator. Update with time. We log when we were doing that, and then again, also just call in the estimator. So, basically a wrapper class around the estimator with the additional logging and stuff we want. Same thing for add vision measurement, sample at, very simple wrapper methods. The differential robot odometry is going to look very, very similar. It creates a differential drive pose estimator, of course. Again, getting the differential drive kinematics from the robot config class. Implements all the same abstract methods, get estimated pose, reset pose, update with time, add vision measurement, sample at. Very similar approach. So the way 3061 lib is designed is that whenever any code needs to know where the robot is, it will invoke the static get instance method on the robot odometry class, and then it will call the get estimated pose method to determine that. And that way, that responsibility is neither in the vision subsystem or the drivetrain subsystem. It's just in this one class to avoid a lot of coupling. The vision subsystem, we will see later, invokes this add vision measurement. The drivetrain subsystem, as we'll see later, invokes like a lot of the other ones, basically the rest of the methods. So that is the robot odometry singleton and the custom pose estimator interface.